All right, welcome to The Explainer. Today, we're going to pull back the curtain on the secret behind the mind-bending power of quantum computers. We're talking about something called super parallel computation. And trust me, it's a concept that's set to change, well, pretty much everything. So before we jump into the future, let's take a look at the absolute best we have right now. What you're seeing here is the Earth simulator, one of the most powerful supercomputers on the planet. I mean, these things are just engineering marvels, right? They can crunch billions and billions of calculations every single second. But here's the thing, even for these beasts of calculation, there's some problems that are just too big, so complex that they hit a brick wall. We're talking about a computational wall, where finding an answer would take thousands, maybe even millions of years. It's just not practical. Okay, for a real-world example, get this. A team set out to crack just one single number, a 232-digit one. It took a supercomputer using over 1,700 processor cores, 3 full years, running 24/7, just for one number.
So that really leads us to the big question, right? What is it about these problems that makes them so ridiculously hard for even the fastest machines we know how to build?
Well, the answer, as it turns out, isn't just about building a faster version of what we already have. No, it's about throwing out the rulebook and completely rethinking the most basic piece of the puzzle.
You know, every single computer, your phone, your laptop, it all runs on what we call classical bits. The easiest way to think about them is like a light switch. It's either off, that's a 0, or it's on, that's a 1. And that's it, it's one or the other. But a quantum computer? Oh, it uses something else entirely, something way, way more powerful. It's called a quantum bit, or qubit for short. And its wild ability to be in a combination of states at the same time, well, that's the key that unlocks this whole new world of computation. This really strange, but incredibly powerful property has a name: superposition. Now, let that sink in for a second. This means a single qubit isn't just a 0 or a 1. It is, somehow, holding the values of both 0 and 1 at the exact same time. This diagram here does a great job of showing what we mean. So a regular bit is like being stuck at one of two spots, the North Pole for 1 or the South Pole for 0. A qubit, though, it can be any point on the entire surface of this sphere. That's not just two options, it's a nearly infinite number of possibilities, all wrapped up in one. Okay, so one qubit can be two things at once. That's cool, but how does that one weird trick lead to a total computational revolution? Well, it's not about just one qubit, it's what happens when you link them together.
You see, a single qubit is interesting, for sure, but the real magic, the secret sauce of quantum computing, is what happens when you start linking them up. And the power doesn't just add up, it grows exponentially. So you take just 10 qubits and link them, suddenly you can process 1,024 different values all at the same time. Okay, that's pretty impressive. But watch what happens when we scale up a little. At 50 qubits, that number just explodes. We're talking over a quadrillion different possibilities, a 1 with 15 zeros after it, all being held in the system at the exact same instant. And if we go to 100 qubits, the number becomes, well, it's just astronomical. It's more combinations than there are atoms in an entire galaxy. That is the unbelievable scale we are talking about here. And this is the secret, right here. This is the whole game. When you perform a single operation on those qubits, you're not just doing one calculation. You are doing that one calculation on all of those trillions and trillions of possibilities at the same time, in parallel. That's what we mean by super parallel computation. So how do you do that? Well, you use something called a quantum gate. Now, don't think of a physical gate. It's more like a command, a carefully aimed pulse of energy, for example, that changes the state of all those possibilities at once. One command, trillions of calculations. Okay, so this massive parallelism is amazing, absolutely incredible. But it also creates a brand new problem. If you have trillions of answers all floating around at the same time, how do you find the one you're actually looking for? Yeah, just think about that for a second. Your computer has literally just processed a quadrillion potential outcomes. How in the world do you pick out the single correct answer from that ocean of possibilities? Well, you can't just look. That's the weird part. The moment you try to measure it, the whole system just collapses into one random answer.
So to get around that, quantum algorithms use this really clever three-step process to coax the right answer into the spotlight.
And this right here is the final, absolutely brilliant trick up its sleeve. It's called quantum interference. The best analogy I've heard is that it's like noise-canceling headphones. The algorithm is designed so that all the wrong answers basically cancel each other out, like destructive waves. At the same time, the wave for the correct answer gets reinforced, making it louder and louder. So when you finally listen, when you measure it, that's the one you're almost guaranteed to hear.
So what does all this mean? What's the point of all this incredible computational power? Well, this isn't just some weird science experiment. This is a tool that is literally going to help us forge the future.
Just think about the possibilities. We could simulate molecules with perfect accuracy, which could lead to brand new medicines or hyper-efficient new catalysts. We could design revolutionary materials, building them up from the atomic level. And on the flip side, yeah, this kind of power could also crack the encryption that currently protects, well, pretty much our entire digital world.
So the big takeaway here is this. Quantum computing isn't just about making faster computers to send emails quicker. It's a completely new way of calculating things, a tool designed to solve problems that we used to think were fundamentally impossible. We are standing at the dawn of this revolution, and it really leaves us with one massive, exciting question. What impossible problem will we choose to solve first?